So the theme today is going to be Christmas because my daughter, Lexi, the one that's in Finland, is actually, as we speak, in Santa Claus Village in Rovaniemi on the Arctic Circle. The picture on the left, this right here, are all the letters from Santa across the world. This is her team, and obviously she's one of the only brunettes. And this is just a picture of Santa's village in the nighttime during the middle of the winter when it snows. So now we'll get on to math. We're going to be talking about variation functions and mathematical models. Okay, there are three different ways to write an equation with variation. The first is y, oops, didn't want that. Y equals kx, where k is called the constant of variation. An example would be b varies directly with the square of m. So b varies directly with the square of m. Varies inversely. So varies inversely would be y equals the constant over x. An example of that would be b varies inversely with the square root of m. So b varies inversely with the square root of m. And varies jointly. So just think about joints sticking together. Jointly is just multiples multiplied together. So varies jointly would be y equals k, then this would be x, z, whatever. So an example of that would be b varies jointly. So b varies jointly with twice m, the square of j, and let's change that to z and z. So, variations worksheet number 1, let's see how this works. The number of pounds you weigh is directly proportional to the number of kilograms you are. So the pounds you weigh is directly proportional to the kilograms. I like to use letters instead of x and y because it just helps me remember which is which as I'm working through the equation or working through the problem. Kay Dent steps on a scale calibrated in kilograms and finds that she is 50 kilograms. She knows she weighs 110 pounds. A, write an equation expressing pounds in terms of kilograms. So I know that she has a relationship. I don't know what K is, but I know we know the relationship between pounds and kilograms. So if I were to solve this for K, I would divide by 50 and get 2.2 would be the constant of variation. So now I'm not done. I need to put it back into this equation. So I'm going to take K and put it back into the original. So P equals K times G. B says, how many pounds would a person be if the scale read 100 kilograms? So how many pounds would I be if the scale read 100 kilograms? And actually, I know the constant of variation is 2.2, so I know these pounds would equal 220 pounds. Excuse the dogs in the background. Okay, so what if the scale read 25? So 2.2, I'm going to plug in the kilograms, and I get 55 pounds. C. So, what does 2.2 stand for in the real world? Well, if I were to solve that original equation, so this equation, and just get the constant by itself, I would get P over G equals 2.2 over 1. So what it stands for is 2.2 pounds per kilogram. Okay. Let's move on to mathematical models. You're driving home from a friend's house on the other side of town. When you are 11 kilometers away from home, you have driven 10 minutes. When you're 8 kilometers away from, you have driven 15 minutes. Assume this is linear. So write an equation that models this situation. Well, so let's talk about mathematical models. Model is just another way to say write a function, write an equation. So I'm going to write an equation, and since it's linear, I know to write a linear equation, I have to have a slope and a y-intercept. But all I have right now are kilometers and minutes. So I need to figure out which is the dependent and which is the independent. So what is my x variable going to stand for, and what is my y variable going to stand for? X is my independent variable, and kilometers is going to depend on the minutes I've driven. So kilometers is actually my dependent, and minutes is my independent. Now, why do I need to know that? So that I can make my coordinates. So my x first is 10 minutes, 11 kilometers. The second one is 15 minutes, 8 kilometers. I'm going to find the slope. And if you remember, slope is y2 minus y1 over x2 minus x1. So my slope is -3 over 5. I'm now going to use point slope form, which is y1 y minus y1. It doesn't matter which point I use. 1 here just means the first point, 2 means the second point. So y minus y1 equals the slope times x minus x1. And I'm going to distribute that. And I'm going to add 11. So now let's continue with the graph on the next page. So to graph this, I'm just going to plot the y-intercept, which is 17. Don't forget, this is what I plot first, the 17. Now I'm going to do the slope, which is rise over run. I have a -3 rise, so I'm going to go down 3 over 5, down 3 over 5, down 3 over 5, and that will be my graph. Answer question C. How much further do I have to go if I've been driving for 25 minutes? Okay, remember x stands for minutes, so y is the kilometers, -3 over 5. I'm going to plug in the 25 minutes plus 17. This is going to equal -15 plus 17, so I have 2 kilometers left to go. D asks what the slope and the y-intercept stand for. Well, the y-intercept, which is the ordered pair 0, 17, stands for at 0 minutes, I'm 17 kilometers. Well, let's be a little bit more specific. Okay, I am 17 kilometers from home. The slope, which is -3 over 5, means for every y over the x, don't forget this is delta y over delta x, for every 3 kilometers takes 5 minutes. 3 kilometers. Takes 5 minutes. E. When do I get home? Well, I get home when I'm at 0 kilometers, so I'm going to do it backwards this time. 0 kilometers equals negative 3.5 times some amount of time plus 17. I'm going to subtract 17. I'm going to multiply by the reciprocal. So I will get home in 10.2 minutes. The last question, F, asks for what a real-world domain and range would be. So I obviously have minutes, but I can't go negative in minutes, right? And I'm going to get home at somewhere around here. So my real-world domain is going to be from 0 minutes to 10.2 because that's when I get home. My real-world range, well, I go from 0 to 17 kilometers from home. So that would be my real-world domain and range. You guys have a great night.